do it anyway.
That's great.
Evaluating for ground truth, it gets like a poor score because it's like total insertion. But if you actually look at it, it might look better. What the fake mask was that was misregistered or missignaled.
It's really funny how like some of the nonlinear stuff gets stripped up just with the initial kind of translation thing, right? Like it flips it or something, and then like we got like because we had that like at my old place we did FSL's like nonlinear registration and the linear registration, and we had to be really careful with the linear one so that like when you're going to the group template, I think we actually had to shift the group template a little bit, or shift the sort of subject template to the group template because
as like an initial
yeah.
Oh yeah.
Otherwise you end up with like something that's just like all folded in it. But it's crazy because then like one of these algorithms, I think we used ANSYS actually, and ANSYS is really good, and like I can actually like account for regions and brains when you like shoot into a group template. It does a really good job. But like this simple initial alignment sometimes it just don't.
Hey Dave, would you mind very quickly going to the link that I posted? Oh, okay. Weird. I just updated the link in the Google Calendar. Yeah, I'm talking to this computer.
I think at some point everyone talks to the computer.
It's just all right.
I'm still trying to find it.
There
The
we
Google Duplex stuff with the voice. Just
Say it again?
the Google Duplex thing where it like talks. They trained the algorithm.
I did not know.
Voice like assistant. It's insane.
No, that's pretty cool.
It's like an assistant. I feel like examples they gave was like scheduling a haircut appointment for a client.
Oh, I've seen that.
Oh,
That was nuts.
Were you able to find the link on,
Like,
I got it.
on the Google Calendar?
realistic
Okay,
pauses.
because I just updated that. The other link was
I
not.
just refreshed the page, so yeah, I got you. I can see your face.
Great. All right. Oh yeah, no. I'll tilt it towards you just a sec. I'm just gonna let people know. Hey, we moved to another channel. Please visit.
One watching, it's just me.
Thumbs down.
Yeah.
Get off
The
the
worst.
stage.
All right. I think we're ready to go in just a second.
Yep.
Yeah. I'm gonna do.
That's pretty good. Good angle stuff.
Is that a good one? Yeah. I'll just give you a little more space. There we go. Perfect.
You got it.
Yes. All right. And I'll just monitor this thing too.
I know there's two. It's fun. Have my day. Oh, three. What?
Oh,
now?
no,
We
I
got people, we got
prefer
three.
if I could take this.
Okay, fine. You did pay for it.
I did.
All right, you want to start?
Should I close the door?
Yes. All right, guys, welcome to Brainhack Day 2. We're going to get started with John's awesome talk about deep learning and TensorFlow.
I already predicted it's going to be awesome. That's great.
I know it's
Deep learning for that. So I'm going to be quickly introducing is the key word here, deep learning and how you can use TensorFlow to apply deep learning to hopefully like some of your problems in the future, any of your applications. So deep learning obviously has generated tons of buzz. You can pretty much use the word and somebody will now hand you $1 billion to start a company. Imagine if you threw something like blockchain into it too, you get another $1 billion or something double. I'm specifically going to be focusing on some of like the deep learning as applied to medical image analysis research. So this was my area of research. And just to show you some examples of what deep learning was able to do, this is all done with almost the same artificial neural network structure. It was able to segment the prostate gland in MR images, able to do the brain in these CT images, segment a mouse brain in MR. It may look bad, but this was only trained on 2 mice. So it did a pretty darn good job for having just a data set of like 2. This one is segmenting the brain into different tissue classes. Here is detecting fractures in bones and CT images. This one is actually generating what a CT image would look like for this given MR image. So you're predicting what the CT image, so that's an application of image synthesis. Another one is just detecting like parts of the mouse that actually anatomy. And then this one is actually just an example of denoising. But the key thing here, these are all done with deep learning techniques, and they are actually all done with the exact same architecture. So you have a decent amount of flexibility for doing these things. And these things are incredibly powerful. So if you already have like a background in machine learning, deep learning, and you want to just see some examples of using TensorFlow, this is the quick thing you can do to start getting going. I have these examples already on the Brainhack Google Drive. So the key thing is to install TensorFlow on your favorite virtual environment in Python, or if you have Anaconda, you can put it on there. And then there's all these examples that you should just be able to run in a Jupyter notebook. So after that, if you guys tell me you want to go to sleep, you can start working on those, you can, but this is the outline of the what I'm going to be starting with. So briefly, let's start with what is machine learning in general. So machine learning really can be broken down into two kinds of tasks. One is supervised learning or unsupervised learning. And then you can kind of stratify these into, well, what is your domain? Are you working in this discrete case or this continuous variable case? So in the discrete case, you're looking at classifying things in supervised learning. In the continuous sense, you're looking at regression problems. In unsupervised learning, well, that turns into clustering and, well, some kind of dimensionality reduction in these others. But I'm going to be focusing on supervised learning here in anything that I'm talking about. So supervised learning is the case where you have your data coming in, but you also have some kind of annotation or some label for that data. So this was either performed by some human expert, or you have some like clinical data, which also probably came from a clinician. Something where you have an input and your output is already defined, as opposed to unsupervised learning is where there's no real output given in advance. So no ground truth kind of. What do these look like in terms of like a simple example? Well, classification is really the task of finding some way to separate your two classes of interest. For instance, this line here, can you learn what this decision boundary is that separates these circles from these crosses? Whereas regression would be, well, what's a function or something, a line that actually best fits all these circles? So here, this is just like a linear regression, and it finds the best fit line. Well, what does this look like in medical image analysis? Classification looks like this. Basically, you're given two images. Can I just say, oh, is it a brain? Is it a prostate or something? So these are real, again, discrete classes that these are known ahead of time, and somebody has labeled these things as saying that. Regression, on the other hand, might be, so, oh, given a brain, can I predict the age of that person or something? Or something like a cancer risk for this prostate patient. I'm just throwing things out here. Segmentation is a specific form of classification. This is actually performing classification on a voxel-wise basis. So in something of neuroscience application that might be of interest is, given a brain, can you parcelate it into the Brodmann areas or something? Again, these are just examples. And you could use like atlas-based registration to do the same method, but you could do deep learning as well. Another example is just, can you find the prostate gland? So any machine learning, supervised machine learning, really fits into this one general framework that starts with, well, I have my input and my output data. I have my model that I want to learn, and this consists of a whole bunch of parameters in there. Well, then I have an objective function, something that tells me whether my model is good or bad. And that's evaluated with respect to ground truth. But then what you have to do is you have to get your model to be good at doing that. And the way to do that is through optimization. And there are numerous techniques. The most common is probably gradient descent on this. But everything fits within this like basically a circle here of learning, okay? So things flow from the input, you get an output, you evaluate how that compares, and then you optimize your model based on your loss function. So deep learning fits within that category too. It's just a particular flavor of machine learning. So if you want a good introduction to deep learning, this Nature paper, this review article is a great resource because it has basically all the seminal papers that are on the subject, and it has a very good explanation from probably the 3 biggest names in the field that pioneered the rise of deep learning. So highly recommend checking that one out. Basically what deep learning really is, it's just a form of representation learning. It's learning features. And you can really think of features as things of like images that are like edges, and you're building up a hierarchy of these things. So edges become groups of edges. They become overall features that make up components of things. So think if you're looking at like a brain, it's not just the edge of the cell side, then it becomes the form of the cell side, the shape, and then you get like regions of those things. And what's important about deep learning compared to some traditional methods is that these features, whatever is learned, actually comes from the data itself. It's not like a handcrafted feature. It's not something that was derived based on like human interpretation or experience. So it really should be, in theory, tailored best to your data if it can learn it well. And the features of deep learning that really make this possible and make it so successful is this like highly non-linearity of these systems. Also, a lot of degrees of freedom make this possible. So, history of deep learning. Artificial neural networks, they've been around for a long, long time, okay? So these things were 80s, 90s, they kind of got dismissed. And you can see one of the key things for training your algorithm is this backpropagation algorithm. It came all the way from 1986. So the computational framework has existed for a long time, but we only started really realizing the true benefits of this in about 2010s, when there was this one paper called AlexNet that had this tremendous jump in performance on this image classification challenge. And that really came about because they were able to have massive amounts of data existing. So that really comes from our use of cell phone cameras, the internet, having all this data available. And then GPUs, so basically video games, have driven the innovation of this because they have this massively parallel computation for which to drive this backpropagation algorithm. And then others have also argued that the development of like optimization algorithms like stochastic gradient descent. And so finally, though, it's really all been wrapped up in this democratization of AI. Almost anyone can do it because of these toolkits, these frameworks developed by Google and Facebook, like TensorFlow and PyTorch respectively, that can make it so easy to learn these models, build these models, and use them and apply them. So these are just 2 among many toolkits, but these are probably 2 of the most popular that are really used in literature. So artificial neural networks they're inspired by biological networks. And so what it is you take a bunch of inputs and you have an output. And this gets basically translated into like a graph-based execution. So here we have some inputs with variables x, they lead to outputs. Inside are these model weights, okay? This just defines a function, okay? And this is the basic foundation of what artificial neural networks are. So what makes it deep, though? Now we just add tons of layers into the middle, all these interconnected layers, and that's it. That's what deep learning is. And again, this fits right into our framework here. So this deep model just fits right into that box of there. And within this box, there has been all kinds of innovations, and people have been like trying to create more complex networks all the time. And so there's lots of space in there to develop things, but there has been a lot of work and a lot of research, and this is where the field has been exploding. You can abstract this down into this concept of layers, though. Layers is, you'll see this going into the discussion of Keras. Everything is based on like layers of these networks, and these layers can be composed of various functions. And some of the main ones that are used here are convolutions, activations. I'll go through a few of these in detail next. And then depending on what you want to do, these fully connected layers, these are these dense things that go around and help you make your decision. But these can be combined in different manners and chained together. And you can do many, many layers as much as pretty much your GPU will allow you to do, really. So convolutions have been the backbone of image processing applications. Again, these were the ones that really took the field by storm. And what a convolution does, if you're not familiar with it, is it basically takes this idea of a kernel and it operates over an image or a grid in this manner. And so what you get is basically a response at each point in the image. But what it does is it says like, oh, I don't care where that response is in the image. If I detect a similar type of response, it could be anywhere, but this kernel will be tailored to that type of response. And so with these networks, they learn optimal filters tailored to the data. And so this is an example of what was learned from this AlexNet one that won the image competition back in 2012. These filters were shockingly resembled activation patterns in the visual cortex of humans, or monkeys, I guess. And so that got people really excited that these things can kind of mimic the visual system. So that was just an interesting result. Yes.
What are you showing there? What's the?
So those boxes are all these like individual kernels.
Yeah. Okay.
So imagine that operating over an image. What it does, these ones pick up like edges, okay? So this one's almost like a vertical edge. If you're going, let's say you're going over a brain, that would do like horizontal edges. It would have like a high response just of where it is.
So those are the kernels that were used in
That were learned, yeah.
Okay.
That were learned by that network. And they're shown in colors because these were RGB images, they're cats, dogs, and stuff like that. So they have kind of, which is interesting that like half of them were gray, which meant they had like kind of equal scale on red, green, and blue. So those are really kind of like strong edges. These other ones had like preference for certain color channels, as you can see. But these were what were learned. And these things were determined by the algorithm and the optimization to be the most salient features that could be looked for to discriminate between the various classes that were included in that image.
So just to be clear, you start with like a random kernel and then okay.
Yeah.
So each one of those little squares is a hidden neuron that represents the kernel?
So each square is one component. So think of all these as being one hidden layer together, but they kind of operate independently. So you get a response for each one of these, and then the next layer will build off of a combination of all of those. I'll have a good visualization for you in a second to hopefully elucidate that. The next one is activation functions. So these nonlinear activation functions are what give neural networks their power, surprisingly. Surprisingly, the middle one here has been the most effective. It has also this discontinuity, which is interesting because you have responses that come in, and what this does is it squashes anything that's negative and makes it zero, and it only shoots out the positive ones, which tends to work really, really well in practice. And it has like beneficial properties of encouraging like sparsity in your solutions and stuff. But it works as a very good nonlinear function activation in the network, okay, without much explanation of. Pooling, this is a layer where you actually kind of reduce the resolution of your data. So you take it from a neighborhood here, and you are able to take, in this case, max pooling will take the maximum value in each of those neighborhoods. So again, what this does, this allows you to build a hierarchy of your data. So if you think of each one of these things as a response to those kernels before, well, now you can learn like how these responses happen over space. And this is really, again, applied to imaging, but you could think of other features you could aggregate this with too. So looking at these things together, pooling, aggregating all these, you have your red, green, and blue channels of this dog image. And so what you have these convolutions, these squares operate over this, and they get different responses, okay? Then you apply your max pooling. In this case, this reduces the resolution, so that's just a low-res version of that. And then you apply this activation function, the rel. You can see anything that's probably negative is probably the blacker the images just gets dropped out there. And then this process is just repeated for numerous layers. The deeper and deeper you get, you tend to get better hierarchy and better results. It's also harder to do. I'm going to try to show this interactive example here. Oh, good. Yes.
How do we interpret the negative side of the activation function? I don't understand how we can have a negative.
Well, think of, so if you were looking for an edge and it looked one way and it had a, let's say you had a white side and a black side, okay? And your filter looked for that and it was trained to look for white, black, okay? It would have a positive response because it matches that. Now, if you go to the other way, if you have white, black or black, white, but your filter's still the same, that would just be the opposite. Okay, because your negatives would multiply by your positives.
So it's okay. So it's some sort of subtraction.
It's basically the true operation is a correlation. It's a sliding window multiplication.
Okay.
So they call it in like signal processing convolution. This is the true use here. It's not convolution. It's correlation. Because in convolution you flip your kernel, that's the only difference. But that's all it is. It's basically a sliding window that multiplies the values and you get a whatever the multiplication is of that. And that's your response. So that response could be positive or negative. And they get rid of the negatives as a nonlinearity.
And the more positive that response is, the more it gets multiplied by your activation function.
That's kind of what happens in this like training process. If you have a high response, oh, that means it's responded well to that feature, and that would have a big difference in your loss function or so. And so it would keep getting tuned more and more in this iterative process towards that feature. So if you had a lot of like vertical edges, you would learn filters that respond strongly to that.
And how does that differ from the weights that are applied?
Those are the weights.
Oh, those are the weights.
Yep.
Oh,
Those actual values of those kernels are the weights in this case, in a convolutional sense.
gotcha.
Okay. Oops. So this is an actual example of this convolution. Anyone want to pick a number?
7.
7?
Yeah.
Oh, it's a good one. It's close to a 1. So here it is down here. That's my input. This is the idea of the sliding convolution windows that we're asking. So you can see this one is, I guess it's a 5x5 or a 7x7. But what the second layer here shows the activation map. What it does is it slides over. You can see that convolution window has the different responses. You can see kind of the color of it. It's how well it responds there to those things. You can see this. You can't actually see what those filters were here, but you can kind of guess what they are. This one responds fairly well to like vertical edges here. This one to like these diagonal edges. Here's that max pooling, so it just aggregates these things. And then what gets really crazy now is in this next layer where now it's not only just a single filter, but these next filters are basically filters of filters. It's a combination of all of your layers below you. And then that happens, you do a pooling on that. So these are, again, responses of filters. And you have responses to that. You can see here, while I could interpret basically what those filters were here, I have no idea kind of what's going up here because it's this aggregation of lower level
You
features.
see that the hierarchy gets better as you go up.
The response. Ooh, your final output typically gets better the deeper you go. Yes, but it is almost impossible to interpret.
Right.
So that's a big challenge, interpretability in these things. These things traditionally, I say traditionally in the past like 10 years, are black boxes. Okay? This layer is what's known as like a fully connected layer. You can see this layer, every single value here is dependent on every single value in that feature map, okay? So that's a giant matrix, all weight parameters that are tuned to this problem, okay? And again, another layer, and your final layer is fully connected. And this is where the decision is made. So you can see this one made the decision that it was a 7, and its second most high weight was a 3. You can see if you erase a little bit of this, maybe it'll get towards like a 1 or something. Yep, see, I think that's 1, it still does 7. But this is kind of cool illustrative example to play with on this. Yeah, close it before I kill my computer.
Does the number levels are decided how?
It's heuristic at the moment. It's up to you. There are some very popular networks that have driven kind of the standard in the field for that. So things that have done well on these challenge data sets tend to get reused.
Makes sense. So I'm really curious about tools that have been used to improve interpretability. I don't know if you'll talk about this later.
I'm just going to mention interpretability as a problem, but without getting away from it.
Okay, I might bring it up later. Yeah,
I'll talk about interpretability in a
cool. Interpretability of neural networks.
minute.
Just some other,
Yeah.
I gotta go fast, I think, and try to do another 5 minutes on this. But some tips for training, though. Really, handling your data is going to be about 90% of your work. Getting your format of data into your network is the biggest challenge in any of that. And unfortunately, I can't give you like a single tip because everybody's data is mostly unique. But really, once you understand like the basics of neural networks and how to program them in like Tensorflow or Keras, that's the small part of your job. It's super easy after that. But other key issues just to think about, again, I'm throwing these terms out there, you got to look them up on your own, really, what these things are. But data normalization and standardization. Think of this as like if you were doing standard, like any kind of fitting, a lot of times in your data, you'd remove the mean. Well, you got to do the same thing here into your data because that's critical for the training. Data augmentation is critical often because these things have so many degrees of freedom that you still don't have enough data, even if you have 1 million images. We especially don't have that in medical imaging and any biomedical application. So data augmentation is some simple things. It could be geometric, just flipping the images left, right, rotating them 90 degrees or in other increments between that. Dropout is a technique that people like to use to improve generalizability or regularize the network. And that just randomly drops out these connections within the neural network. And you're adding basically a ton of nonlinearity to your network when that's happening. But it's in practice, it works well. Some other things, just more key terms, more methods are with low sample size things, transfer learning is useful. That's where you actually learn on one different type of images or different type of data. You basically pre-train your network and then retrain it from there. Instead of starting from random initialization, you start from that. That's helpful because like in medical imaging, we have such a lack of data. Well, we might as well leverage all the cats and dogs that people have took with their cell phones on the internet. And it surprisingly works well, shockingly. These ideas of autoencoders are big. Generative adversarial network, GANs were developed 2014, and really they were a hot thing. Residual networks, these allowed networks to get super deep. So 150 plus layers. So now you're just getting like out of control with these things and number of parameters. But again, people are just like beating the depth thing to the depth, like
The depth horse.
depth to death. Something of interest to neuroscience applications is there's a lot of like temporal data, so like fMRI data. Well, you could use recurrent neural networks. These basically are a sequence of things. So A becomes your black box or your network model. And what it does is it learns based on what it's previously seen, and then it learns in a sequence. You can go actually both directions, bidirectional, but what it does is this may be the model itself may be common, but you unroll it and you have now the sequence of how that model can be trained. I don't work much with that, so I'm definitely not going into detail. Long-term, short-term memory models are another kind. These have this like added feature of forgetting involved, so you can have these like longer-term and short memories and stuff for that. But again, key terms, look them up on your own. Pitfalls. It is absolutely critical to validate and partition your data into separate training and test sets. A lot of people in computer vision like to do 3 sets, training, validation, and a totally separate test set. Sometimes that's not totally possible in our data sets because we're so limited, in which case you might want to do just 2, like a training and a validation, but do a cross-fold validation on that. But whatever you do, avoid data contamination. even if you're not using the same image, but if you have the same subject in there, mistakenly from your training and your test subject, even if it's not the same image, your network might be able to learn the specifics of that subject, and you might get biased results. They tend to overfit. Why do they overfit? Well, because of this graph here. These things have millions of parameters. What I like to hear, this was like, the size of this was actually the most interesting thing. These are the number of those trainable weight parameters. These ones like VGGNet are up to 155 million parameters. That's crazy. You think of like the equivalent of fitting a regression line to something, which is 2 parameters, a slope and an intercept. This one is 155 million parameters. So you can really overfit to your data like crazy. That's especially the case in low sample size problems. So other methods might be better than deep learning, like random forests. And this was a workshop I attended over the summer. So I encourage you to check out this website to get a really great perspective on the biomedical application of machine learning. They have some great discussions about trustworthiness and all explainability and transparency of these models, especially because of the concerns that they're black box approaches. And these are just some other good resources that have been really good. The textbook has a lot of theory. The middle book has great practical application of Python using TensorFlow for deep learning. I don't think it's been updated to TensorFlow 2, but it has been good in the past. And the Coursera course by Andrew Ning is very good. You can just audit those ones for free if you want, but they're a great introduction to from a leading expert in the field. So finally, let's try to get to some TensorFlow basics. So why TensorFlow out of all the others? I kind of went with TensorFlow personally because it had these advantages, I felt. It had a very good high-level programming API. You could develop these models very rapidly. And that became even more the case with Keras, which is just Keras is basically a standard programming interface for this, and TensorFlow implements it. What TensorFlow is really great at is it allows you to seamlessly run your code on any of the different computing platforms, like your CPU, your local GPU, or you can do that on a cloud GPU. And if you get really fancy, you can run it on Google's custom tensor processing units, the TPUs. So these are optimized specifically for TensorFlow. So if you want to run a project and you buy resources on Google Cloud, you can run it on their TPUs. And it should be the exact same code. There's a lot of people have contributed models, trained these models, and made them publicly available. So there's a rich ecosystem. And importantly, in my thinking, was that this library or this framework was supported directly by Google. So you have billions of dollars of investment in this. So TensorFlow operates as a graph, as a data flow graph structure. What this means is, so if I have a function, I want to represent this as a graph, it would look something like this. So you have variables in blue, your X and your Y, like the orange represents a constant there. But this is what TensorFlow does with any of your operations under the hood. But they make it so it's in fairly easy syntax. You don't even have to worry about that. This is created all automatically for you. But just be aware, this is what's happening under the hood. And what you used to have to do in TensorFlow 1 was this graph had to be fully created at the time you wanted to run it, and everything had to be known. But now with TensorFlow 2, they have what's called eager execution. So you don't actually have to set up the whole graph and run it. You can just instantly get your results up to a certain point of wherever you are in defining that graph, which is great. It makes it more intuitive. It's more like if you were using something like MATLAB. And the TensorFlow APIs kind of are built around this hierarchy. There's the low-level functions that can just be found in like TF. Any of these are the basic operations. They used to have, in TensorFlow 1, they had this layers function, which was very similar to Keras. Luckily, they got rid of it, and now everything is just Keras. Okay, so stick with Keras. If you're learning TensorFlow 2, you're going to be golden. Okay, that's what it is. There is a little bit of confusion about these estimators. Estimators is a framework for really training, testing, validating your model. It allows you to do that rapidly. A lot of people at Google use it. It's a little bit cumbersome to get started with. So I guess my recommended use would be to develop your models in Keras by itself first, and then if you really wanted to scale these things, you could deploy it as an estimator. So these estimators can leverage anything in Keras as building your model, but it's a fairly cumbersome framework to learn. I really like it, but for starting, you can write all your models straight in Keras, and that's what some of the examples that I try to give are. So where does this all fit into our framework for machine learning? These are the key things that you have in Keras. So you have the Keras layers. They have some predefined models that can basically just do these layers for you. You have your loss function, the most commonly used loss functions. You have your optimizers. There's a whole bunch of flavors of those. And this, again, is probably where most of your work is going to come, to me formatting your data in some way that the model can read it. Luckily, in the examples that I have here, these just come in as basically NumPy arrays. But just think of if you could get it to a NumPy array, you should be able to translate these examples that I show directly for your use. TensorFlow also has this thing called TensorBoard, which allows you to visualize the training of your model. So here you can see how the loss function behaves as it's training. You can see the accuracy on a validation set. In the case of images, you can see those as they're coming along. So this is the input, that's the ground truth, and down there is the result. You can also see what your model structure, your graph structure looks like. So you can click on all these and delve into it. So it's a very powerful set of tools for you to use. So finally, if we want to start looking at some examples of how to use this, I broke these all down. These are all on the Google Drive, and so they're all accessible as IPython notebooks here, or Jupyter notebooks. So just to give, this is basically like a hello world version of TensorFlow. So this one you can find, this one's under the basics here. You fire that up. As soon as you have your environment all set up for TensorFlow, all it is basically importing it. And again, I got really excited by eager execution, so that's why it's like highlighted so much here on my thing. Because before it took a lot of legwork to actually just these awkward calls to set up your session, start your graph, and run it. Now I can just define these tensors, in this case these constants. I can print them, I can see the values. I can multiply them. So in this case, I'm just multiplying x times x, and then I can visualize the result. Or you can just get it as a NumPy array, and now you're back in NumPy. And so essentially you can also set that from NumPy. Here's a simple matrix operation. So this, I'd like to argue that TensorFlow could be used now in TensorFlow 2, really like a general computing environment, much like MATLAB. You get all these nice features of all these matrix operations, but you also get this seamless under the hood. It could be run on a GPU or so. So all your computations could be that. So you can leverage all the functionality like that. But this one is just making a matrix. I'm going to multiply it by that vector x. So I created a random 4x4 matrix. And here, multiply m times x, get your result. Again, you can visualize it as NumPy. Here's some other operations. So with TensorFlow, you can use their programmatic one. So to add x to itself, or you could just write it using overloaded syntax. So again, we're getting kind of like MATLAB here. But again, the beauty of this, which I love so much, is the eager execution. Now I can just see the result as it comes up. No need to actually run a graph, which was a pain in the butt. This has made TensorFlow very usable and intuitive now.
What do those constants mean? The tensors?
Which one, right here?
Yeah.
Just random values that I gave it. So I defined that up here. I gave the constant. So the concept of a constant is that it's a not changeable weight in your thing. So in this case, it's just if you had a bias value that you wanted to put in there or known or something in your equation, you would define it as a constant. Here I just did it because that was a variable that we could put it into TensorFlow. So I just set it randomly here. But these could be scalar values, anything. Now nice, I think this was a pretty good example here. An example of doing a linear regression. Here again, this one is actually going to use Keras to build the model. So what it does here is it created this like linear class. So this just extends the Keras model objects, okay? And what it does, it has two variables. So this is different than constants here. Now that you mark them as variable, now you know that these are trainable parameters, okay? So all we have here is our slope and our intercept for this. And here is this is like, you have to follow this syntax for Keras in the model. This is basically what the model is. So this is defining y equals mx plus b, okay? Or wx plus b here in this case. So I just gave it a fake data set here with 2,000 points. And I gave it a known slope and intercept, and I just added some noise basically to it. So you get a plot like this. Again, think of now our general framework for machine learning. I need to define a loss function, and I also define a gradient here. So how to optimize that. And you'll see the key terms kind of here. Here you see the TF gradient tape. This keeps basically a running record of your loss, how it changes. And this is what gets optimized. You'll see it get applied down here. There are apply gradients. But these are, again, the big components of the machine learning framework. So you instantiate that model that we created up here, our own. You get a standard optimizer here from Keras. So I'm going to optimize some loss function, which we define. So this one gets the gradients here from your inputs and your outputs. So this is actually the input data here that we defined here. So we're getting at this data. That goes into your model here, given your model, and then you optimize it. And you tell it what parameters to optimize here. You can do things where you can just have your list of all variables, but this one's very explicit. So if you run it, it will train everything. You can see the loss function print out every 20 steps here. And you can see the loss starts at 69, goes all the way down into 0.94. That just tells you basically the least squares loss, what you see. But what do you want to see your final parameter values? Well, you can get now that W and that B, and you can see it's really close to what the initial function was, the 3 and the 2. And you can just plot the result there too. These examples were lifted straight from the Tensorflow tutorial. So you can run them directly on their webpage using their Codalab, which is their own IPython thing. But these ones are actually the digit recognition example. So these ones are, again, here, this data set is called MNIST. It's a famous data set, very simple. Here, this one uses the TF-Keras, the sequential model. And all that says is now I can define a bunch of layers in a sequence. So remember, this is just that recipe of all those components we talked about before. Here, the flatten. So instead of operating in that convolutional operations, this one just flattens those 28 by 28 images into a single vector. And then we have these dense, fully connected layers. And look, they even threw dropout in there for us. Here, you can specify, because it's within the model framework, all you have to do is specify the name of the optimizer you want, what your loss function is, and if you want to output any accuracy metrics, just as you're going along and training. So you can see those printed out here. But the model.evaluate is kind of like any of the scikit-learn like functions like fit and stuff. So you can put your test data in. First, you got to train it, actually. Excuse me. So there's fit to your training data, and then you can evaluate your test data. So it just follows that syntax. You put data in, get your data out. Here, you can see what your final accuracy was down at the bottom on your evaluate. So this one was able to get 98% accuracy on just this very simple network.
Super quick question.
Yeah.
Is it common to mix activation functions like that?
Yes, it could be totally user dependent on your design, whatever you want to do. The last layer is usually unique because that's your final classification layer in this sense. So you usually want this like softmax that goes between a 0 and a 1, whereas a ReLU gives you 0.
Infinite, yeah.
So, but it's very simple to do. You can just add more layers on top of that, like that, essentially, and you could retrain it as simple as that. Slightly more complex one is it's the same problem under advanced, but now it does that convolutional operations that we showed the visualization for before. So almost the exact same thing as we saw before. Here they go a different way of building it. So they take more of that linear model approach that we saw for the first one. This one builds your own model, and you can see that you have a convolution layer here. So you can see this is the chain of it. So it makes the components there itself, but this is what puts them in that order. So you have convolution followed by a flattened, and then a dense layer after that, and then you return all of these. So it goes. Basically, this is exactly that. I think that image that we saw, or that visualization that we saw with the digits. Again, you have your loss functions, your optimizer here. So simple to do once you see it. Again, here's the creation of your gradient tape. This is a little unintuitive to me, even, but I think once you get the hang of it, it just becomes a standard, like almost recipe for these things. Yeah. Here is your loss function here, and your training now. So this one trains in different steps here, and you get your loss metrics out here again, so you can test the accuracy on your test set, and you can almost see. Let's see, this one, yeah, about the same level of accuracy as the other one, but just imagine throwing more and more layers on there, you'll get better and better. And it's almost trivial to do that. Let's see, I don't know how much time I have left. Oh, 11:30.
We might, like just over 5 minutes.
Okay.
Yeah.
The last things that I have are just more complex examples. Again, these were lifted from the TensorFlow website. So the classification one is classifying different kinds of close images. So this gets into just, can you classify these images in different categories? Well, maybe you have the same things with like functional connectivity things or something. It's just, again, it's just a matter of reformatting your data into basically these problems here. And again, the model building phase is so quick and easy. Training might take you a while. Make sure you have a good GPU on hand because you're training these millions of parameters. It's going to take a while. But really, you can leverage these existing techniques very simply. The final one is just a regression problem. This one is predicting, I guess, fuel efficiency given a few variables of data from cars. So just imagine instead of having car data, you had a table of some kind of clinical data or some functional measures. You could do similar things with the variables and just create your models as simply as that. So again, here they just do simple building of this dense model. It's just a bunch of these matrices that are connected to each other, and then they get one value out. So they're trying to predict miles per gallon as their final answer. So again, this is this continuous data sense versus trying to predict a kind of class. Here they have actually the nice model summary, so you can see what these things are. Again, you could get the results. You can see the training loss and everything on these things. So these examples, I think, in summary, really give you the building blocks of what you can use for Keras and TensorFlow. And can't iterate enough. It's just getting your own data into that format is the key. And that's all the challenges that there are to it. So lots and lots of people are doing this. And I think TensorFlow is ripe to be used as a general computing environment now, especially now that TensorFlow 2 came out. So, any quick questions while we still have a few seconds, sir? I know this was trying to cover a lot, but.
Is it a fair statement to say this is mostly about pattern recognition? So if I think for our PET scans, we generally see that people just have all over the place, higher or lower uptake. So I'm guessing with the normalization, you're gonna lose that aspect anyway. So would deep learning still be valuable in that context, or would you say, nah?
I think it could be, as long as you properly control for whatever your normalization is. So there's so many different methods that you could do to kind of preserve that relationship. So what's nice, I guess, is that if there's high or low uptake, well, that could be relative to surrounding anatomy or something. So if there's like a pathology there, that is the thing of interest. If these things build up like a high enough or a deep enough representation of that, well, it's going to recognize that that's low with respect to the surrounding anatomy. So that might be good too. Or something like PET, where you do have like absolute counts of like uptake. Well, maybe you don't normalize at all. So it is the absolute values are important. So you can get away with that stuff in like, because CT imaging, actually, those units have values, Hounsfield units, whereas MR imaging is really just all relative. So you can get away with not doing any normalization of CT images because everything's relative, but you have to do normalization for CT or else, for MRI, because they're all over the place. So it's really problem dependent. You just kind of have to think about what it is, what it's doing. That's a problem. A lot of people just blindly apply these things, and they can get like good results on their test set too, because it's their data set. Because say I have all my MR images are from the same MR scanner here at Yale, it'll work. I didn't have to worry about normalization. I just got lucky. But as soon as I applied from a data set from another site that had used GE instead of Siemens, bam, I'm done. It didn't work. So medical imaging is very challenging. You got to be very thoughtful about the imaging modality input parameters too. So.
I have a question, and I think we have like 1 more minute. So if anybody else has a question, you can jump in. I don't know if you'll be around here a little bit.
I can stick around, sure.
Yeah. So we'll have one talk after yours, and then we'll do lunch and people can chat. But any other questions from people here?
Yeah, I have a question. So how do we determine the number of layers? So the number of layers is really correlated to the deep learning. How do we define if we should choose deep learning or regular learning machine methods, where we have only a few features to?
There unfortunately is no rhyme or reason, really. There is no theory at why depth, what the best depth should be. It really is trial and error. And what people have tended to do is they kind of follow the recipes of things that have worked on these like big challenge data sets. So, which is an interesting thing is, well, the networks that succeeded, those things tend to get propagated as like building blocks. Okay, so you follow a whole bunch of convolutions, so you follow that recipe. Well, maybe that's only tuned for that data set. It might not work for yours. You might have another one that is better or more ideal. So there is no reason for what you do other than trial and error. Again, these things fit so well to the data that you give it. You might look like you get really good results on your set and your test set, but then if you try it on something else, you get poor generalization. In which case, you have your 150 million parameters, you overfit to your data, you look great, but then like something stupid like a linear regression might actually do better in the general sense. So there's no rhyme or reason to how many parameters, weights that there are, what's the right one to use, unfortunately. Other than try it. You'll find an optimal probably. I have no advice other than that.
That's great. Excellent.
Do you want to switch over just because the computer is kind of like the
I
video?
will not be in the shop.
Oh, okay.
Yeah, fair enough.
We can also. Oh yeah, I'll just move it so it gets the
Just
screen.
like the screen.
Yeah. I'm glad you're monitoring this. Let's just do that. Seem okay?
No, perfect.
Excellent. All right, so guys, we're gonna have a conversation about some clinical neuroimaging tips, pitfalls, etc. Saria?
Hi, everyone. So yeah, this is going to be a much less technical talk than what John just did. In fact, to some extent, I'm going to purposely skip over some technical stuff. But it sort of relates to his point at the end about blindly applying these models. So you really need to think especially in a clinical context, about why you're asking these questions, like what question you're asking and why you're feeding it into this complex algorithm, and what different things can be affecting the result that you get to make sure that you're really studying what you think you're studying. So here we have a typical workflow for predictive modeling or machine learning study. And this is taken from this 10 Simple Rules paper led by Dustin that we published in Neuroimage earlier this year. And you can just see the really basic steps. So of course, you're going to acquire your data, you're going to pre-process your data, you're going to choose a model and a validation strategy, train and evaluate the model. Depending on how you're doing it, that may involve some sort of parameter tuning as well. You're then going to validate your model, interpret your results, and of course, share the model and the data. And so as you can see, there's sort of these rules that are associated with each of these steps, which are from this manuscript. And so I'm going to be using this as sort of a general framework to talk about some do's and don'ts today. And so while I'll be talking about this general workflow, I'm also going to be really talking about it within the context of clinical modeling. So I'll be using this schematic from a separate recent review, which is on clinical modeling specifically in addiction, but it really would apply to any disorder. And so here you can see that in addition to the general machine learning steps of acquiring data, such as selecting the algorithm and running the model, I should point out Steph helped with this beautiful figure.
Oh.
We also have additional steps that we need to consider for clinical prediction. So defining our treatment outcome, collecting longitudinal data, and ultimately really improving clinical care, which tends to be the actual aim of clinical predictive modeling. So from time to time, I'm also going to be referencing these steps to highlight specific considerations for translational imaging. As Steph said, this is meant to be a conversation, so please do interrupt if you have questions.
So when you say predictive, this is you have your training data set and then you use it independently.
Absolutely, and I'll get into different methods of validation, cross-validation, and so there's like internal cross-validation and external, and yeah, so this is just basically talking about anytime you use a machine learning or a predictive, cross-validated predictive model, but specifically in a clinical context. Yeah. And I'll also be referencing some data from one of our recent clinical papers using a connectome-based predictive modeling approach to study an addiction outcome, just in order to walk you through an example of a real-world clinical data set and sort of the decision points that come into play there. So going back to our original schematic, we can see that the first practical step of our workflow is, of course, to acquire your data, or in the case of a secondary data analysis, maybe just identify your data set. So there are several considerations related to this process. The first and most obvious of this is just to define your problem or question of interest, and then select or design your data set and your overall approach. The problem or question of interest for the data set I'm talking about today was really straightforward. We're interested in identifying a network that would predict a treatment outcome in addiction. And of course, the word predicts here is key because true prediction requires cross-validation in an external sample. So by using the term predicts to define our problem, we're essentially following rule number one, which is the first rule proposed in this paper, which is just to use out-of-sample prediction to generate more accurate and generalizable models when it's studying brain behavior associations. And so to start to answer this question of can we identify a network that predicts treatment outcome, we collected data from a group of patients that we scanned prior to entering treatment for a 12-week RCT. We scanned them before treatment and again following treatment. Really briefly, some of the clinical characteristics are going to come up again later. So all of the participants for this study were methadone-maintained individuals for opiate use disorder, but they were now entering treatment for co-occurring cocaine use disorder. So this was a pretty clinically complex sample. For this sample, we had a couple of different types of neuroimaging data, including multiple tasks and also resting state data, which meant that we had to choose which of these three imaging data sets to start with in building our brain behavior model, because at the time, the approach we were using wasn't optimized to incorporate multiple tasks, although I believe Dustin and others have worked on that since. And the reason we wanted to, and we chose to use task data because there was evidence coming out, as reported in this great paper I'm recommending here by Abby Green and others here, showing that really brain behavior models generated using connectivity data collected during performance of tasks tends to outperform connectivity data collected during resting state. And just because of what we knew about cocaine use disorder at that time, we went with our reward task data versus our cognitive control task data. So in addition to selecting our neuroimaging data, we needed to select our behavioral variable of interest. We wanted this to be a real world clinical variable, and we wanted it to be dimensional because we wanted to be able to really capture heterogeneity in the data set and not just look at something like yes, no treatment completion, because lots of different factors and go into whether or not someone completes treatment. They can achieve abstinence and drop out of treatment. It's unlikely, but it does happen. And this brings me to rule number 6, which is that we need to be mindful of our sample characteristics. So you need to understand how the behavioral variable that you're trying to predict varies across the sample, because that's going to have implications for the statistical approach. And you also need to determine if it's representative of the larger sample in general. So in this case, in the case of a clinical study, not everyone involved in this parent RCT was eligible for neuroimaging. And so what we had to do is we wanted to make sure that the overall distribution of our treatment outcome was the same in the neuroimaging sample as it was in the overall RCT, because otherwise it might not be very representative of the actual treatment. Luckily it was. You can see that it was a very skewed distribution. So a lot of people sadly didn't achieve any abstinence. So you can see a 0% abstinence on the left. The good news is that the approach we're using can handle non-normally distributed data, but it's just something we need to be mindful of. And we're going to talk about that more later when we get into actually running our model. So look at your data is basically the take-home point. Okay, so the next thing, of course, we need to do pre-processing. I'm not really going to talk about that much today. I think most people here are probably familiar with basic pre-processing, and there's some recommendations, again, in the review manuscript. The one thing I do want to talk about very briefly is the output of pre-processing in this example data set, because it turned out that we had a really large number of individuals that had to be excluded for excess motion. And this is a great example of checking to see that you're predicting what you think you're predicting. So things like motion can really affect feature selection, et cetera. And so, this led us to sort of a decision point. So we started with 72 individuals, 19 of them had excess motion, which is a lot. And so the obvious answer is just exclude them. But actually this brings up some interesting questions of sort of, are you going to bias your model? So obviously the pro of excluding individuals with excess motion is that you're minimizing motion effects from feature selection. So you're probably more likely to really get the features that matter and not just motion artifacts. However, a con of this is that you might unintentionally bias your sample. You can imagine, especially in a clinical population, that patients that have a hard time staying still in the scanner might be the patients that have a more severe course of the disorder. And so by excluding them, you're really, again, going to bias your model. So you really have to think about what the implications of excluding people for different reasons are. What we chose to do here is we excluded them from the feature selection phase, but then we also included them as part of our replication sample to see if the model that we built in people with acceptable motion generalized to the individuals with excess motion, and it did. So that's sort of one solution.
A really great solution.
Thanks, Ted. So now we need to, of course, choose our modeling approach. So there's a lot of different modeling approaches, some of which, well, we've heard about a lot over the past 2 days. They all have different strengths and weaknesses, and the appropriate approach is always going to depend on your question of interest. So if we go back to my question of interest, it was, can I identify a network that predicts outcome? Meaning that I didn't want to just predict outcome. I wanted to identify neurobiological targets that were associated with that outcome. So I chose to use an approach called connectome-based predictive modeling, developed by Todd's group, which allows for one-to-one mapping back to network anatomy, unlike a lot of other approaches. In other words, it's both a method of generating individual behavioral predictions from neuroimaging data, but also a method of identifying networks observing specific behaviors. So it's possible that I could have selected a different approach that would be more of a black box, that wouldn't have let me understand as much about the anatomy, that might have had higher predictive accuracy. But the question I was interested in wasn't just, can I predict an outcome? It was, can I identify the connections that are associated with that? So there's always going to be a trade-off to some extent between interpretation and potentially how accurate your model is. Some sort of neural network might have been more accurate, but I would have had a lot of trouble interpreting it.
Yeah.
So this is really just to highlight that the way that we framed our question had significant implications for how we selected our modeling approach. So of course, now that we've chosen our approach, we need to train our model, which includes choosing a validation approach. So of course, total independence of training and testing data, so like data from 2 totally separate clinical trials, is optimal. But the practical limitations of clinical research often mean that the acquisition of multiple independent data sets is just it's just not going to happen. No one's going to fund you to do that. So in the absence of multiple data sets, the classic approach is just to use some form of k-fold cross-validation to separate a single data set into training and testing data sets. So the data set is randomly divided into k equally sized non-overlapping subsets. And these are used to iteratively assigned as training data and then applied to the testing data, and you rotate through. So a really simple example of that would be split half, where you're just literally saying where k would equal 2, and you're just splitting it into training and testing data and developing the model in the training and then applying it to the test. Another really common approach is leave one out cross validation, where k equals your sample size. And so you're just iteratively taking each person as the testing person and training the model on everyone else, and again, rotating through. These days, things like 5-fold cross validation and 10-fold cross validation are really common, and those are just examples of when k equals 5 and 10. I would argue that for small heterogeneous clinical data sets like the one I've been talking about, something like a leave one out cross validation approach is probably best, because it does allow you to leverage all the data for model generation. And it also avoids this need to balance split halves for other variables or even just other folds in general. So for example, in this study, I didn't really talk about it, but people were assigned to different arms of behavioral treatment. So you could imagine if I randomly split my sample in half, it could be that in my training data set, I have a bunch of people that were assigned to one behavioral treatment versus another. And that's something that I would actually want to account for. And so this prevents us from having to do that. Of course, there's also a lot of limitations to leave one out cross validation, in that, as with all methods, it may overfit the data, but especially leave one out cross validation is prone to this. So again, there's always a trade-off. For the data set I'm talking about today, which was small and quite heterogeneous, we did use a leave one out cross validation approach for model generation and initial validation. However, we combined that with an external out of sample replication strategy that involved data from a separate clinical trial. And I'll talk about that more in just a minute. So this is another sort of compromise. We also have to choose our performance metric. So there are a lot of different ways of validating model performance. They all basically involve comparison of predicted versus actual values. And the exact metric you choose is, again, going to depend on your question of interest and always needs to be defined ahead of time. And it's also going to depend on whether or not your data are continuous or categorical, which John touched on previously. So the metric you choose will depend significantly. Bye.
Hi, Dustin.
I think he looked at the food and didn't see anything he liked.
He's probably looking for this. Don't tell him I have.
In all cases, where you're using an internal cross-validation scheme, when you're assessing significance, you need to use permutation testing. I guess except for split half, but every other time you would have to use permutation testing, right?
Yeah, it'd be hard to, assess those intervals with split half.
Yeah. When you wouldn't need to, because they are independent.
Oh yeah. Okay.
Where was I going? Okay, so going back to this. So again, our performance metric is going to depend on our question of interest, and it's not always, and not all metrics are created equal. So it's going to depend on what your clinical question is. So as a really general example, and sometimes a bias is okay. So as a very general example, you could imagine where you're trying to build a model to decide whether or not to assign someone to a treatment as usual or some sort of novel intervention. And whether or not you want to maximize sensitivity versus specificity might be really dependent on the relative effectiveness of the treatment as usual, and also the relative riskiness of the new intervention. So it all is very contextual. Just to drive that point home a bit more, this is an addiction example because, again, I'm an addiction researcher. So here on your left, you have models, so these are confusion matrices, and on your left, you have models with high sensitivity and low specificity. And then on the right, you have models with low sensitivity and high specificity, but these are shown across two separate outcomes. So one is assignment to active methadone treatment. And then the second one at the bottom is termination of active methadone treatment. So deciding that someone no longer needs to take this medication and they're going to be okay without it. And what I've done is I've highlighted in red the cases for which overdose risk is highest. And so you can see that for case number one, the overdose risk is minimized when sensitivity is maximized, but for outcome two, overdose risk is minimized when specificity is maximized. So in other words, assuming that the overall goal of addiction treatment is harm reduction, which I hope it should be, then a model with high sensitivity but low specificity might be acceptable for predicting initiation of medication, but might not be optimal for predicting termination of medication. And vice versa. And it's also really important to remember that other measures, so things like balanced accuracy as opposed to just overall accuracy, are important. I'm going to talk at the end about some resource.
How do you get to this? Is this just like
So this is,
a helps history?
oh, sure. So this is, I'm trying to do math in my head. This is a sample size of 110 people. And this is an example of a categorical, this is just like a fictional example, but this is an example of a categorical classification where we're just saying yes, no, assigned to treatment. So if we just look at the top left square, we have the number of true positives written by this model. So that's the number of people that we said, yes, we should assign them to treatment, and it turned out we were right, and they responded well to that treatment. And then below that, we have the number of false negatives, and so those are the ones where we were wrong. So we said, yes, assigned to treatment, but it turned out, oh wait, false negative. Those are the ones where we said, no, don't assign to treatment, and it turned out we were wrong. They should have gone into treatment. Then we have false positives, which are the individuals that we did send to treatment, but it turned out they weren't responders. And then we have true negatives, where people we said they don't need treatment, and we were right. And so based on that, you can calculate various different other metrics, such as sensitivity and specificity and things like accuracy and balanced accuracy. And I'm not going to go into all the different ones today, but very often you want to go further than just accuracy, and I'm going to give some references for resources to look at that. But you can see like the proportion of individuals assigned on the top and the bottom that have true positives or true or false positives, etc., is the same. But which model is optimal depends on the question of interest.
Mm-hmm.
Does that?
Yeah.
And these are confusingly called confusion matrices because and it's just because it's referring to the bits that the model was confused about, basically. So the bits that the model didn't get right. This is a summary of that. In clinical research, they're called something else. So now that we've done all of that, we may want to. Oh, okay.
It's the food.
Okay. Bye, staff. We've trained and evaluated our model. As part of that, we may want to tune some parameters. I'm not really going to go into that much today. If we were using like a nested cross-validation, that's something that we would do. But just a really simple example of that, not in a nested sense, is that, for example, if we wanted to adjust like the threshold we're using for feature selection. So in the data set I've been talking about today, we used an initial threshold of P05 for feature selection, which is pretty general. But we could have also tried multiple different thresholds. So we might have said we actually only want things that are really significantly associated during our feature selection phase, and done like P01 or P001. And if we'd done that, we would have to correct for the fact that we had run 3 different thresholds when we were evaluating the model accuracy. So this is, again, just another version of, just like if you run multiple models, you need to correct for that in your multiple comparisons. If you run the same model with multiple different parameters, you also need to correct for that. Finally, having trained our model, we're ready to validate it in an external sample. As I mentioned for this one, we sort of cobbled together this really heterogeneous external sample. So about a third of them were also taking methadone like our original sample, but the rest were only cocaine dependent. And somehow, amazingly, our findings still managed to replicate to this pretty heterogeneous external sample. Which I think speaks to sort of the robustness of using a leave one out cross-validation approach, or not necessarily leave one out specifically, but using some sort of cross-validation approach in the beginning. We didn't overfit our model, and then therefore it generalized to an external sample. Finally, now that we've validated our model, it's essential for me that we interpret our results. I think that's critical for all models, but that it's particularly essential for clinical models. Because I think that elucidation of biological mechanisms of recovery or even disease progression can be used to improve current treatments and develop novel interventions. However, interpretability really is one of these primary challenges of predictive modeling in general, and of brain-based clinical models in particular. So approaches that yield these really robust predictions may nonetheless not do much to advance our understanding of the underlying biology of the disease. So just briefly, I want to talk about some recommendations for enhancing interpretability of findings generated from these sorts of models. Within this context, we can think about our data as having multiple levels of interpretation. The most basic of which is in the context of a connectome-based prediction would be individual connections or edges. And we can often think about this, those edges or connections also within the context of sort of regions or nodes that these edges are connecting. We can also summarize all of that based on its overlap with known brain networks in order to facilitate interpretation and ultimately elucidate some sort of mechanism. So I think putting everything into the context of a theoretical framework is really important. So that then we can, and that's what this error was doing. It's saying that once you've sort of really understood your results and proposed a theoretical framework, you can then use that and apply it to a novel data set to try to further refine our understanding of the clinical problem. So obviously there's lots of different kinds of predictions. So I'll just go through 2 examples really quickly. So this is an example if you were doing like just a simple classification using like a support vector machine, and your input was just a priori brain regions. So you have like however many brain regions, and you throw them in to predict your outcome, and then you, or to classify, and then you assess performance. And then a lot of times people stop there and they say, oh, we did it. We figured out who responded to treatment and who didn't. But they don't really talk about what was really going into that model and what the significant predictors were and what they meant. And part of that is because very often many methods don't, it can be hard to sort of map back from the predictors, from the model result to which predictors are really driving that. And so one really easy way to start to get at what is contributing to your model is to just repeat your model, leaving out selected brain regions. So you can repeat your model, excluding all, you can exclude your model, excluding, for example, just only prefrontal regions, and then assess the accuracy of that, and repeat that in an iterative nature. So you can see, how accurate is my model if I leave out the cortical regions, or how accurate is it if I leave out prefrontal regions. Similarly, you can also get at the performance of individual regions alone. So you can say, I'm only going to include my subcortical regions and see if it's accurate. And so these are all sort of just post hoc follow-up ways of trying to get at what was really driving the significance. And then you can update your theoretical model. If we use something like a connectome-based approach, which, as I've been saying, does allow for this one-to-one mapping back to the individual connections, we still need to do some work to really try to understand what it is that we've identified. So we can identify these really dense networks, we can assess our performance, and we can even summarize them based on connections with known canonical networks. But very often, these networks are just really hard to interpret. And so I think it's important to try to understand them within a context, within a theoretical framework. So I skipped a step. And so in addition to just summarizing and based on overlap with known connections, we can take something like a virtual lesion approach, which is essentially what I was describing in the last slide as well, where we're just knocking out individual networks and repeating our model to see how well it can predict without those specific connections. And again, to update our theoretical model. So for example, in our study, we found, the network we identified was very dense, but it did have a lot of connections that were consistent with some canonical networks and with more general models of addiction, and it seemed kind of interpretable to us. And our hope in proposing this model is to really encourage other people to test it in their own data. I mean, we've released the actual networks themselves, but sometimes this sort of theoretical understanding can be useful for encouraging others to adopt this framework. That does bring me to an important point of setting realistic expectations. So we were quite happy with this model. We were like, oh, this makes so much sense. Like, it involves like coordination of reward and salience networks that probably like are related to motivated behavior, and then this thing of like coordination of attention and executive control networks, and this all makes perfect sense in what we know about addictions. Wonderful. But then Sarah Lichtenstein did some really nice work where that's just currently in press, where we find that our fabulous cocaine abstinence network really doesn't relate to opiate abstinence at all. And we can identify totally separate networks, even in the same individuals that are subserving different substance use behaviors. So this is just an example of setting realistic expectations. So not all traits or brain states or populations are going to fit a single model. We think this dissociation is really cool and points to, again, this overall aim for me of clinical predictive modeling, which is to improve clinical care. So by refinement of existing models. So existing models in addictions have traditionally focused on the same brain regions as subserving like all addictive behaviors, but some of our data suggests that may not be the case for opiates and cocaine. And then finally, we have our last step, which is, of course, to share our model in the data. So you can download our networks. Data aren't out. We have not shared the data yet, actually, now that I think about it. But we have shared our networks, which is more than a lot of people do. I just, right before I finish, there's just a couple more like clinical considerations I want to point out. And this sort of goes back to this point about setting realistic expectations. So timing matters, right? Like the time course of a given disorder is often highly nonlinear. Like in addictions, multiple failed treatment attempts are common. That's just kind of standard. So, scanning someone early in the course of treatment or after they've already started some abstinence can be really important, and you may have different models there. It's also important to consider sort of the clinical implications of when you scan. So a lot of neuroimaging studies in addiction traditionally try to scan people before they enter treatment. But actually often that means delaying the start of treatment so that you can schedule them for an fMRI scan, which in the context of something like opiate use disorder is arguably not very ethical. And so that's fine. You can just scan them once they start treatment, but you just have to acknowledge that what you're doing is it's not a pre-treatment scan. You're looking at predictors based on patterns of brain response during early treatment. But again, that model then may not apply to if you scan someone while they were actively using. Similarly, in the clinical context, it's important to separate out sort of prediction versus etiology and mechanism. So very often things that predict aren't the same as things that traditionally distinguish patients from controls. In other words, things that predict treatment response may not be the things that are causing the disorder. And people often find that kind of difficult to understand, but you could imagine that something like motivation to change might be a significant predictor of treatment response, but that's not necessarily the thing that is actually going to initially cause you to have that disorder. And similarly, the things that predict may not be the same things that are changing with treatment. So again, something like motivation to change clinically might predict someone's treatment response, but during treatment, how well they do might depend on acquisition of new skills, and that's what's changing during treatment, and therefore networks that are associated with that are the things that are changing. So again, just that these things aren't, one model won't fit all. These are just some resources. I'll put all these slides up on the shared drive. They're not there yet. These are some of the papers that we talked about. This last one at the Shinehouse Sensible Rules talks more about different metrics for evaluating continuous models. And this preprint from Richard Dinga talks about different metrics for categorical models, so sort of moving beyond accuracy, particularly in a clinical context. We hilariously, in our review paper, cited that paper, and the reviewer said, we really need to talk about this important new preprint. And we're like, we did. Thank you. Some more resources. These are some books that could be helpful. I think some of them might have already been mentioned. Websites. Again, I'll put this all on Drive. Twitter can be a resource. Sometimes, people have access to other resources that you haven't thought of. So I see all the time people posting, does anyone know a good intro to deep learning for someone that has no background in X? And on that note, I found this yesterday, which I thought was so cool. I've never used it, full disclaimer, but as someone with like a really small lab that doesn't have like millions of coders, the idea of this seems great to me. So basically you can sign up and you can tweet and find someone that will help you check your code. So you could tweet, wanted someone who understands sport vector regression in MATLAB. It's about 50 lines of code. You do like a short description and then they just direct message you. So I have no idea if it works, but it seems like a really cool idea. And yeah, I think that's it. Thanks, everyone.
Any questions? So you talked about validation with the independent sample. What if you're so for our data set we have baseline and longitudinal, and one of the things that might be worthwhile is to look at the baseline characteristics to try and predict a categorical outcome at 2 years.
Mm-hmm.
Is that something that this particular model?
Absolutely, and if you have multiple time points of neuroimaging, what we've done is we've taken the model that we generated using pre-treatment data, and we've applied it to post-treatment data to predict longer-term abstinence to see if that works. There is a bit of circularity there because it's the same people, and so you obviously need to be really mindful of that.
That's what I was wondering, what's a different model you have to account for that?
Well, I think it's okay to see if your model is stable over time by applying it to the second time point, but a lot of these things, it's just about, again, contextualizing it. So that's not an independent replication. That's just a test of whether or not your model is stable in those individuals. Yes. You know what I mean? Which is quite different. Yeah, if you have, in terms of different internal validation schemes, depending on your sample size, yeah, you could use something like just to leave one out cross-validation, or something like a 5-fold cross-validation might be good.
Is there a rule of thumb for the number of people within each division?
Well, there's this there's whole papers on it. I can send you some papers about, but yeah, there's sort of like a trade-off between. Dave, do you want to make talky sounds about trade-off and sizes of K?
There are a
Someone
lot
else?
of different rules of thumb.
I'm done.
I'm Dave. There are a lot of different rules of thumb. I think that there's that one cool figure that talks about some rules of thumb sample size for different machine learning techniques, and we can circulate that.
Oh, there's a paper that just came out from Whelan and is that who you mean?
It could be. I've only seen the figure from it circulated, but we can send that around. But there really is not a good answer. There are certain sample sizes where you're definitely going to overfit your data, but usually we're not talking about those sorts of sample sizes.
I think like you really have to be conscious of like there's different levels of overfitting. Like I think I kind of talked about this a bit yesterday, but there's big side effects in fMRI, so you can overfit to your site. There could be high motion in your data, you could overfit to that. There could be aspects that are more biologically related that you wouldn't directly consider as noise, but can lead to overfitting. Like if all your data is from college-age students, at Yale, and they're between 18 and 22, I would find it difficult to believe that model might reproduce in an older sample of people from maybe lower SCS backgrounds or something like that. So there's multiple levels of overfitting. So your N kind of would be a function of it depends on what you want to where you want your model to reproduce, right? If you want it to be really, really global model, you're going to have to accurately sample all of the sort of different kinds of people you might want it to represent, right? I mean, honestly, with a linear model, you might end up having to have different linear models for different for men, different for women, different for 20-year-olds, different for 30-year-olds, right? And so the overfitting is not just as a function of noise, it's also as a function of how much variability is represented in your cohort, right? So all of those things will go into sort of deciding what your N is, and that's before you even get to the point of figuring out if I've got 1 million parameters in 10 subjects, so obviously that's not good enough. Before you even get to that point, you have to consider if you're adequately sampling all the different kinds of people you want your model to represent.
And also just, I was going to say just much more generally, I mean, great points. There's a trade-off of you want enough data to train to really accurately generate a model, but also while retaining enough to have a decent size for testing, because you can imagine if you only have you can say, oh, I want to train with, 40 people out of my sample size of 50. That sounds great because your model will, 40 is still very small. But, if you say you want to use 90% of your data to train your model, that sounds potentially great. But if your data set isn't very large and 10% that is remaining is quite small, then it may not generalize just because you actually have a really heterogeneous testing sample. And similarly, vice versa, if you have your training sample be too small.
It's really true. I just want to draw something really quickly. I think many of you may have seen this, but just because we've talked about this a couple times, this is the simplest example of kind of a model where you have just enough parameters to fit that you're overfitting. So if you have a linear regression and you just have 2 samples, okay, so I drew the line before even drawing the data. But if you have a linear regression and you just have 2 data points like here and here, you can definitely fit a line that perfectly fits those 2 data points. That's a really good example of overfitting. You have just enough parameters that you can fit, you have just enough data points that you can fit the number of parameters in your model. If you had only 1 data point, you could draw an infinite number of lines to this point. So you actually don't even have enough data to fit this model. So you'd be underdetermined. You could also have a case where you have you have 3 points, but one of your points actually lies on top of this or really close to it because they're highly correlated, let's say. You still have a situation where effectively you have a just well-defined enough model. And that's also an example of overfitting. So these are just this is this very simplest example of somewhere where you might get overfitting.
Lunch?
Yeah, we can keep talking over lunch.
And thanks, Sarah.
Yeah. Oh yes.
Turn off the spies.
What?
Turn off the spies.
Yeah.